Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So our video today, we're going to be continuing with our series on linear algebra in C++. Today continuing to focus on eigenvectors and eigenvalues as we have been doing for the previous two episodes. Particularly what I want to focus on today is using the technique of QR decomposition to actually calculate estimations of the eigenvectors and the eigenvalues for a given matrix. So anyway, I really hope you enjoyed the video. If you do like it, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make my videos reasonably regularly. Just recently that hasn't really been going according to plan, but I do my best, and if you subscribe, you don't need to worry about missing anything. Thank you very much. Right, well, without much further ado, let's jump to it, and let's have a look at computing estimations of the eigenvectors and eigenvalues. So in the last video, we looked at QR decomposition and how we could go about implementing this technique using householder reflections. In this video, I want to focus on how we can actually use QR decomposition to estimate the eigenvalues and eigenvectors for a given matrix. I should say right at the beginning that my focus is on creating code that computes eigenvectors and eigenvalues for symmetric matrices. QR decomposition can be used to compute these for any matrix, but in the general case of a non-symmetric matrix, that requires the use of complex numbers. As it stands, the code in our linear algebra library doesn't support that. So, for now, we're going to stick to matrices that have purely real eigenvalues and eigenvectors. The only matrices that are guaranteed to have purely real eigenvalues and eigenvectors are symmetric matrices, hence the focus on those. This might sound like a major limitation, but actually it isn't that severe. My goal has always been to use this code to do principal component analysis. That is what we're building up to, and in that case we compute the eigenvalues and eigenvectors of the covariance matrix of our data. One great thing about covariance matrices is that they are always symmetric and therefore have purely real eigenvalues and eigenvectors. In later videos, I might go on to look at expanding our code to work properly with complex numbers, and then we can handle the general case, but we'll see how that goes. To quickly recap then, in the last episode we talked about QR decomposition and showed that any given matrix such as A here could be expressed as the product of an orthogonal matrix Q and an upper triangular matrix R. And we went on to look at how we could achieve this in C++ using householder reflections. If you haven't seen that episode, I suggest you go and have a look at that. I'll put a link in the description below as usual. I already mentioned that we are focusing on symmetric matrices, in which case the QR algorithm offers a very simple way of estimating the eigenvalues and eigenvectors for a given matrix. Just to note, when we describe a matrix as symmetric, we mean one where the elements are mirrored across the main diagonal, as shown in this example here, where I have coloured the elements to make the reflection clearer. The actual QR algorithm is quite simple and consists of the following steps. We first decompose our matrix into Q and R. We then form the next iteration of A as the product of R and Q, and then we decompose that into the next iteration of Q and R, and so on. And we keep going with that process until we reach some kind of convergence or a maximum number of iterations. We will have a more detailed look at these steps in the following slides. The best way to illustrate this is with an example. So let's start with the example symmetric matrix that we have used before, as shown here. So the first step is to decompose this into Q and R using QR decomposition, as we discussed in the last video. If we let A0 equal A, then using QR decomposition we get the values for Q0 and R0 as shown here. Note that R0 is upper triangular, as we would expect. We can now form the next iteration of A, which we will call A1, as the product of R0 and Q0. This gives us the result shown here. Now we can decompose A1 into Q1 and R1, again using QR decomposition, which gives the results shown here. As before, R1 is upper triangular. And we can keep going through that process, forming subsequent iterations of A. So I have shown the results here for A2, the second iteration, A5, and A10. Notice that as we work through the iterations, the A matrix is getting closer to being diagonal, by which we mean that all of the elements away from the main diagonal are getting closer to 0. If we look at the diagonal elements themselves, I have coloured them here, we find that they become progressively closer to the actual eigenvalues, which I've shown here at the bottom of the slide. So if we perform enough iterations of this process, we can simply read off the eigenvalues from the main diagonal of the resulting A matrix, which is rather cool. The question is, how do we know when we have performed enough iterations to have a good enough approximation of the eigenvalues? Well, we keep iterating until the A matrix is close enough to being upper triangular. We simply have to decide some threshold value depending on how good we want our approximations to be, and then we can stop iterating when we come to within that threshold of being upper triangular. We will look at a way of actually achieving this when we come to look at the C++ code shortly. That gives us a nice and relatively easy way to estimate the eigenvalues, but how do we then go about obtaining the eigenvectors? In the case that our original matrix is symmetric, we can actually get the eigenvectors quite easily by simply computing the cumulative product of the Q matrices that we get from each iteration of the process I have just described. In this case, the columns of V will now contain estimates of the eigenvectors of the original matrix. Let's look at how that works for our example matrix. In this case, the product of all of the Q matrices from Q0 up to Q9 gives the matrix shown here, and the actual eigenvectors for this matrix, which I've computed using other software, are as shown here at the bottom. If we colour these as shown, we can clearly see the correspondence between the columns of the V matrix and the actual eigenvectors shown below. Let's have a look at this process geometrically to see what is happening more clearly. So here we have the actual eigenvectors for the example matrix A shown in silver. On the left we have the original matrix A, and I have given the actual eigenvectors and eigenvalues for this matrix shown here by V of A0 and lambda of A0. The approximations are shown below. And we are going to start with initial estimates of the eigenvectors based on a 3x3 identity matrix, as shown here in blue, orange and yellow. Now, let's see what happens when we perform the first iteration. After the first iteration, we can see that our estimated eigenvectors have all moved and are already much closer to the actual eigenvectors that we want. As we have discussed before, the actual sign of the direction of an eigenvector doesn't matter, as it is just a scaling by -1, so we don't need to worry if they are pointing in opposite directions. Let's see what happens at the next iteration. So, at the next iteration, the sign of the blue and orange estimated eigenvectors has changed, but all three of the blue, orange and yellow vectors are now clearly closer to the actual eigenvectors shown in silver. If we keep iterating through the process, we can see that with each iteration the estimated eigenvectors get closer to the actual eigenvectors. In this case I've let it run for 20 iterations, and we can see quite clearly that by that point we have a fairly good estimation of the actual eigenvectors. Notice from the display on the left that we also now have a very good approximation of the eigenvalues. Actually, an important point to notice is that the approximate eigenvalues converge to the actual eigenvalues much more quickly than the eigenvectors do. We will come back to that point a little later. Just to be sure that this does work, let's look at another example symmetric matrix as shown here on the left. The display on the left is of the same format as the last example, so we have the actual eigenvectors and eigenvalues, and then the approximations shown below. As before, the actual eigenvectors are shown in silver, and the approximations in blue, orange and yellow. Let's iterate through the process as before. After the first iteration, we see that our vectors are getting closer to the actual eigenvectors. After the second iteration, they are closer still, but notice that they are not converging as fast as for the first example. And if we keep iterating through the process, in this case for 40 iterations, we see that they do gradually converge to the actual eigenvectors. Clearly, for this example matrix, the process is much slower to converge to a good approximation of the actual eigenvectors. But, as for the first example, if you notice from the display on the left, the eigenvalues actually converge much faster. At the beginning of the video, I talked about how we would only consider the case of symmetric matrices, but I want to take a little time to look at an example of a non-symmetric matrix. Some non-symmetric matrices do actually have purely real eigenvalues and eigenvectors, and in these cases the QR algorithm will still give us a good approximation of the eigenvalues, but not the eigenvectors. That is an important point to note. So, let's consider the example matrix that we have used before, as shown here. This is clearly non-symmetric, so let's see what happens if we try to use the QR algorithm to estimate the eigenvalues and eigenvectors for this matrix. So, as before, we have our example matrix and the actual eigenvalues and eigenvectors shown here on the left. And we have the actual eigenvector shown graphically by the silver arrows, along with our initial estimated eigenvector shown by the blue, orange and yellow arrows. As before, after the first iteration, our estimated eigenvectors have moved closer to the actual values as we would expect. But let's look at what happens as we progress through the iterations. Notice that the yellow arrow stops moving after only 2 iterations and doesn't get any closer to the corresponding actual eigenvector. The blue and orange arrows also only get close to the actual eigenvectors, but actually never converge. I've shown only 7 iterations here, but you can already see that they're not going to converge properly. If we look at this angle, we can see that the orange arrow is clearly not converged to the actual eigenvector shown in silver. But notice from the display on the left that the eigenvalues have converged quite well after only 7 iterations. So, in the general case, it seems that the QR algorithm can give us the eigenvalues, but not necessarily the eigenvectors. Luckily, if we have good estimations of the eigenvalues, we can use these to compute better estimates of the eigenvector by using a different algorithm. And we can do this using what is called the inverse power iteration method. So in the first video in this 3-part series on eigenvectors and eigenvalues, we looked at the power iteration method and showed how we could use this to compute an estimate of the dominant eigenvector for any given matrix. This is a good technique, but it can only give the eigenvectors that correspond to the largest magnitude eigenvalue, not all of the eigenvectors. So whilst it can be very useful, it isn't going to work for what I want to do. For the power iteration method, we start with some randomly chosen initial vector, and we simply find the product of the original matrix A and that vector, and then normalize the result. And we just keep iterating that until some stopping criteria is met. The sequence vk will then converge to the dominant eigenvector. For the inverse power iteration method, we simply change the equation that we iterate to this. In this equation, mu is an estimate of one of the eigenvalues and I is the identity matrix. So here we again start with a randomly chosen vector v0. We then subtract mu times the identity matrix from A and compute the matrix inverse of that before computing the product of that matrix and the vector v. As before, we then normalize the result before moving on to the next iteration. In this case, the sequence vk will converge to the eigenvector that corresponds to the estimated eigenvalue that we provided for mu, and so we can use this method to estimate all of the eigenvectors for which we have an estimated eigenvalue. The inverse power iteration method converges to the eigenvectors much faster than the method we used before, even for symmetric matrices. It is therefore the best method to use. So the procedure to follow is to use the QR algorithm to estimate the eigenvalues, which it does quite quickly in many cases. We then use the inverse power iteration method to estimate the eigenvectors corresponding to each of those eigenvalues. We will see how this works in practice when we go on to look at the C++ code. So let's do that now. Okay, so let's take a look at the C++ code that I've put together to actually implement this maths that we've just been looking at. And actually, thanks to the work that we've done already with putting together this linear algebra library, the code that we need to implement the QR algorithm and the inverse power iteration method is actually surprisingly simple. Now, I am aware that there are different ways of writing this code. There are some very clever ways of doing it that are really optimized, that don't necessarily rely on a straightforward implementation of sort of matrix arithmetic, for example. That's not really my focus with these videos. It really, my goal is always for these to be educational, and, I want it to be clear how these algorithms actually work, rather than, focusing so much on going for the most optimized way of doing it. So that's what I've done. Anyway, looking at the actual code, this is the qbeig.h file. If you get this code from GitHub, there's a link in the description below, by the way. This code will be available shortly after this video is released. And so this is the file that we've talked about before that contains the code for the power iteration method that we implemented initially, and so I've simply added to it to add the new functions to implement what we've been talking about in this video today. The first thing is that I've defined two new error conditions with these const expression terms here of QBig underscore max iterations exceeded and QBig underscore matrix not symmetric. I think probably the meaning of those is obvious. And then we have our function to actually implement the QR algorithm to estimate the eigenvalues. Now it's very, very important to note that this is only guaranteed to work for matrices that have purely real eigenvalues. And of course, as we've said before, the only matrices that, or at least as far as I understand it, the only matrices that are guaranteed to have purely real eigenvalues are symmetric matrices. So for that reason, I've actually included a test here for whether our input matrix is symmetric. But we'll come to that in a minute. Let's have a look at the actual code. So we define our function QBIQR. It accepts as input a QB matrix 2 object, a const reference to one of those called input matrix, and we accept an std vector of type T object for the eigenvalues. You're going to return those as a vector. First thing we do is we make a copy of the input matrix. Just because there's still some issues that I haven't resolved yet with the use of consts in the QB matrix 2 class, it's best to simply make a copy of it first. Indeed, that is quite inefficient in many ways, and if you're dealing with really large matrices, you really wouldn't want to do it that way, but it does work. I'll come back and refactor the code at some point in the future. First thing we do is verify that the input matrix is square, so simply if not A is square, return QBig matrix not square. We verify if the matrix is symmetric. If not A is symmetric, return QBig matrix not symmetric. It's all fairly self-evident. I am, however, just for the moment, going to comment this code out because there are situations where a non-symmetric matrix has purely real eigenvalues, and in that case this code does indeed work. And for the examples that I want to look at when we look at testing, I want to show an example for the non-symmetric matrix that we've been looking at before. But generally this code should be enabled, and it's really there just for safety, because as we'll see when we come to test it, if you pass a non-symmetric matrix to this function, it will return the right number of eigenvalues and they will probably look reasonable. But in cases where some of them should be complex or even purely imaginary, then it will give only real values and not the real component of the actual complex number. It will give a completely irrelevant, erroneous result. So for safety, it's better to include this test. But just for the moment, we're going to comment it out. And then we simply extract the number of rows. Our matrix is square, so of course the number of columns is equal to the number of rows. And we create an identity matrix of the same dimensions. There we go, that's pretty self-evident using the functionality from our QB matrix 2 class. We create two matrix objects here, Q and R, to store Q and R, obviously both of size num rows by num rows. And now we're actually going to loop through each iteration. So I've set max iterations to 1,000. For the testing I've done so far, I found that to be sufficient. We initialize iteration count to 0, and we set up a boolean called continue flag, which we initialize to true. And we then loop while iteration count is less than max iterations and continue flag is true. So the first thing we do is we compute the QR decomposition of A. Simply this way, we do collect the return value, but I haven't used it, and we simply call the QBQR function that we've looked at previously with the matrix A as input, and it will put the result into the matrices Q and R that we defined up here. We then compute the next value of A as the product of R and Q, simply A equals R times Q, literally just that. We can do that because the QB matrix 2 class, of course, implements matrix arithmetic. We now check if A is close enough to being upper triangular, and this is what I talked about in the slides before about the stopping criterion for the iterations. And actually we can do that using the isRowEchelon function in the QB matrix 2 class that we created previously. So a row echelon matrix is upper triangular, so we can just use the same test. So we simply do if A is row echelon, if that is true, then we set continue flag to false, which of course will cause us to drop out of this loop. Otherwise, we increment iteration count and we simply go through the loop again. So at that point, when we come out of that loop, the eigenvalues should be the diagonal elements of A, so we can simply read those off, which we do with this very simple code here. And then we set the return status accordingly. So if we reach the maximum number of iterations, we return QBig underscore max iterations exceeded. Now that isn't strictly speaking an error condition. So we do this at the end of the function anyway, so that we still return the eigenvalues that we want, but we return that value simply because that might be useful information to the calling function for some reason. Otherwise, we return 0. Okay, and that's everything that we need to implement the QR algorithm to estimate the eigenvalues of a given matrix. So the other function that I've added here, this one actually performs the inverse power iteration method. So as before, we define our function QBinv PIT. It accepts as input an const reference to an input matrix and a const reference to the eigenvalue. Recall from the slides we looked at previously, we pass the eigenvalue for which we wish to estimate the eigenvector. So we do that there, and then we have a QB vector object, a reference to a QB vector object, for which we're going to return the eigenvector. As before, we make a copy of the input matrix, we test if the matrix is square, we set up a random number generator. Now the reason we do that is that it is good practice to initialize the iterative process with a random vector, simply to minimize the chance of that vector being parallel to the vector that we want to estimate. Okay, so we set up a random number generator that will allow us to do that. We then extract the number of rows from the matrix. Of course, it's square as before. We create an identity matrix exactly as before. And now we create our initial vector v. We simply set up a QB vector object called v of num rows elements. And then we simply loop through every element and we set that to a random number extracted from the random number generator that we've just defined. And now we're actually going to run through our iterations. We set max iterations to 100, initialize iteration count to 0, and we define a delta threshold of type t of 1 times 10 to the minus 9. So this is going to be for our stopping criterion. And what we're going to do is look at how much the vector is changing with each iteration, or how much the magnitude of the vector is changing with each iteration. And if that change drops below this delta threshold value, then we will say that we have converged, and we will accept that as a stopping criterion. We initialize delta with a very high value to start with. Delta, of course, is type t. We set it to 1 times 10 to the 6, or 1 million to begin with. We then define a QB vector object called prevvector of size num rows, and a QB matrix 2 object called temp matrix of num rows by num rows. And then we enter our iteration loop here. So we loop while iteration count is less than max iterations and delta is greater than delta threshold. And the first thing we're going to do inside that loop is to store a copy of the current working vector to use for computing delta. So we do that with prevvector equals v. And now we compute the next value of v, and that requires us to compute a matrix inverse, which we have the functionality to do in our QB matrix 2 class, so that's good. First thing we do is set temp matrix equal to a minus the eigenvalue multiplied by identity matrix. So the eigenvalue, of course, that's the value of mu from the equations we were just looking at. And then we do temp matrix dot inverse to compute the inverse of that. So after this, temp matrix will now contain the inverse of that. And then we calculate the next value of v is simply v equals temp matrix times v. And v dot normalize, and that's it. That's then the next iteration of v. And then we just have to compute delta, which we do is we simply take the difference between v and the previous vector and then take the norm of that. And there we go. Then we increment the iteration count, and that's it. When we drop out of that loop, we simply return the eigenvector that is now stored in v. And as before, we have this little bit of code here just to return QB eigmax iterations exceeded if we dropped out of this loop because we exceeded the maximum number of iterations rather than reaching our delta stopping criterion. Otherwise, we return 0. And that's it, really. That's everything we need to implement the inverse power iteration method. So these two functions together, we can use the QR implementation of the QR algorithm to estimate the eigenvalues, and then we can call the inverse power iteration function with each one of those estimated eigenvalues in order to calculate the corresponding estimated eigenvector. We'll have a look at how that works in a moment. The one other thing that I wanted to talk about is in the QB matrix 2 class. The one function I added to QB matrix 2 is this function here that returns a boolean. It's called isSymmetric. It tells us whether a matrix is symmetric. First of all, we test if the matrix is square. If it isn't, then it can't be symmetric, so that's an obvious condition. And then we test for symmetry about the diagonal. We define two variables called current row element and current column element, which we initialize to 0. We set our return flag to true and initialize diagonal index to 0. And then we're going to loop through, this is our outer loop, we loop while diagonal index is less than the number of columns and return flag is still true. And then we initialize row index to be diagonal index plus 1. And then we have our inner loop where we loop row index is less than the number of rows and return flag is true. Now the reason we've used a return flag here is so we can drop out of these loops immediately if we find one element that doesn't meet the criteria for symmetry. Because once we've done that, we know the matrix is not symmetrical. There's absolutely no need to carry on looping through it. So we get current row element as being the element of the matrix at row index, diagonal index, and current column element as being the element of the matrix at diagonal index, row index. If you write that out on a piece of paper, I think you'll see how that's working. It's quite straightforward, really. And then we simply compare the row and column elements, and if they're close enough to being the same, we would set return flag to false. If they're not close enough to being the same, we set return flag to false, which of course will cause us to drop out of the loops and finish. Otherwise, we increment row index and we keep going, and then we increment diagonal index and loop around the outer loop, and then at the end we simply return the return flag. Now, the one thing to note is the use of the close enough function. Notice I'm not testing for absolute equality between these because I'm allowing for the use of double precision floating points. That's what I will be using this with probably all the time. There's very little point actually testing for absolute equality with those. So we use our close enough function that we've talked about in previous videos to simply say, are these close enough to within our defined threshold of being equal, and if they are, it returns true. If they're not, it returns false. Okay, so that's just another aspect of it that I think is a better way of doing things than testing for absolute equality, which is very unlikely to be met in all conditions because of rounding errors and so on. Okay, that's everything for the QB Matrix 2 class. So let's move on to having a look at the code that I've written to actually test this. Okay, so this is testcode_qbi.cpp, which you'll find in the testcode subdirectory if you get the repository from GitHub. And I've simply modified the code that we wrote before for testing the power iteration method. It was a couple of episodes ago. So everything else here is the same as we've had before. I'm not really going to spend any time talking about that now. We have functions that print a matrix, functions that print a vector to the terminal so that we can see what's going on easily. One difference I have changed here is I changed the set precision and print vector to 6, simply so we get more decimal places when we're looking at the estimated eigenvalues. And this was the code we wrote before to test the power iteration method, so I'm not going to talk about that. And here we have the code I've written to test the new inverse power iteration method. So we test first with a simple 3x3 matrix, and this is the initial non-symmetrical matrix that we've been working with that we know has purely real eigenvalues and eigenvectors, so we can work with that. And we know what the eigenvalues are for that one, which I've calculated those using other software, so I've just put those in here into a vector, initialize a vector with those. And then we set up a vector to store the eigenvector called eigenvector of type QB vector, and then we're simply going to loop through each one of these eigenvalues. So we just have for auto current value in eigenvalues. Okay, so that will just loop through each of those. And then we estimate the eigenvector corresponding to that eigenvalue using the QBInPIT function, collecting the return status into return status. And we pass to it test matrix that we defined up here, and we pass to it the current value, which is the eigenvalue that we're using, and we pass the eigenvector variable into which it will place the result. And then we use the print vector function to display the result. And if our return status was QBIg_max iterations exceeded, we display a message to say that that was the condition under which we stopped. It's not an error, so we don't stop execution or anything like that, but we simply display that message. Okay, and here we have the testing for the new isSymmetric function. Very simple. We pass to it a symmetrical matrix defined there and say whether that's symmetric, true or false, and then a non-symmetric matrix. Notice I've changed as one element, this one from -7 to +7, so that's no longer symmetric, and we display true or false accordingly. Obviously this one should be true and this one will be false. And then we test estimating the eigenvalues by QR decomposition, initially for the initial non-symmetric 3x3 matrix here, this one, and we then calculate. So the way we use that, we set up a std vector object called eigenvalues, and then we call the QBIQR function with test matrix, and we pass the eigenvalues there, and it will place each of the eigenvalues into that vector object. And then we simply display those again using for auto current value in eigenvalues, and we display those out. Note the use of set precision 6 to display everything that's going on. And if we reach matrix iterations exceeded, we display a message. If we're not symmetric, we display a message. Okay? And then we do exactly the same thing for a simple symmetric 3x3 matrix defined here. Otherwise, this code is exactly the same. And here we have an example that should have complex eigenvalues. So this is a non-symmetric matrix that has complex eigenvalues, and we test that as well to see what kind of output we get. And that's it. That's all of the code that I created. So let's go to the terminal and have a look at what happens when we run this code. Okay, so here in my terminal window, I'm in the test code subdirectory. And the first thing we're going to do is compile our code, as it's going to be called test code underscore qbeig, and we compile qbeig like that, and we're going to compile test code underscore qbeig, oops, dot cpp minus std equals c++ 17. Okay, let that run. Okay, now let's run our code. /test code underscore qbeig. There we go. So that gives us all of this output. So let's just have a look through, scroll back up to the top and have a look at what we've got. So the first thing we do is we test the power iteration method. That's what we talked about before, using the simple 3x3 matrix. We covered that before. And then inverse power iteration method, the simple non-symmetric 3x3 matrix. We know what the eigenvalues are, and then we print out the estimated eigenvectors for those. Notice we reach maximum iterations of the first one, but not the second or third ones, okay? But I've compared these to the results calculated with other software, and I do believe those to be correct, at least to the precision shown. We then test the new is-symmetric function, so we pass a simple symmetric matrix. You can see there that it's symmetric, and it returns matrix is symmetric true. We test with a simple non-symmetric matrix, so I change this value here from -7 to +7, so it's no longer symmetric, and it returns matrix is symmetric false. So that's the result we want, that's good. Then test estimating the eigenvalues by QR decomposition, initially with the simple non-symmetric 3x3 matrix, and we get the estimated values of 1.596, -0.372 and 0.026, and we can compare those actually to the values we had here, 1.596, -0.372 and 0.026, so we can see that those are correct. And then we test with a simple symmetric 3x3 matrix there. Okay, and we get the estimated eigenvalues, and then we estimate the eigenvectors for each of those. That's the code we just looked at, and again, I've checked those with other software, and I do believe that they are correct. And finally, we look at the example that should have complex eigenvalues. Now, I really want to emphasize this, because this is where there's an element of danger with this code, because this looks like it's given 3 sensible values, but 2 of these values are actually completely wrong, because they should be complex. And at the moment, our code doesn't support complex numbers. That might be something I come on to look at in a future video, but for now it doesn't. So it gives 3 eigenvalues and 3 apparent eigenvectors, but they are wrong. And to prove that, what I want to do is simply let's go back to the actual code that we have in qbeig.h. Here it is. And what I'm going to do, we're going to go back to the qbeig_qr function, and let's just put this code back in. Now this is really important, really, that this function, this code here, stays in to test if our matrix is symmetric. We'll go back to our terminal. Let's clear that. Let's compile again. And let's run our code. Now, the first thing, let's scroll back up to the top and see what's going on. Here we go. So obviously no change there. That method is all fine. So the first thing we notice now is different is when we come to estimating the eigenvalues by QR decomposition, we pass the initial non-symmetric 3x3 matrix, and notice now we get the matrix not symmetric return, and the estimated eigenvalues are just blank. There aren't any. And we pass a symmetric 3x3 matrix. Everything works as it did before. We get the eigenvalues, and hence we can go on to estimate the eigenvectors. And this example should have complex eigenvalues. Of course, we get the matrix not symmetric return condition and no estimated eigenvalues, which is really what we want. That is the much safer way of doing things. Now, as I mentioned before, it might seem like a major limitation, making this so that we can't deal with matrices that are not symmetric, but my goal for writing this code is to use it for principal component analysis, where we will be calculating the eigenvalues and eigenvectors of the covariance matrix of our data, and the covariance matrix will always be symmetric, therefore this is not really a major criterion. And as I say, in future videos I'm not promising, I might go on to have a look at extending this code to implement proper complex number matrix arithmetic and vector arithmetic, and then we can go and looking at extending it to work in the general case. It should be noted the QR algorithm is not always the best algorithm for calculating or estimating eigenvalues. There are conditions where it doesn't work and it'll just loop around and iterate forever and will never converge to the correct answer. There are some matrices where that will happen. However, I have found for what I want to do, it does seem to work quite well. But again, maybe in a future video that will be something we'll go back to visit. Anyway, there we go. So there we go, that's really everything that I wanted to look at today. So over this video and the previous two videos, we've covered pretty much everything that I plan to do, at least for the moment, in terms of eigenvectors and eigenvalues. We started out looking at the simplest way that we can estimate or compute the dominant eigenvalue and eigenvector using the power iteration method. And then we went on to look at QR decomposition and how we can implement that using householder reflections. And now finally in this episode, we've looked at how we can use QR decomposition as the basis for the QR algorithm to form estimates of the eigenvalues for any given symmetric matrix. And then how we can use the inverse power iteration method to go on to use those to compute estimates of the corresponding eigenvectors. So the next video is going to be on something else. I'm hoping on principal component analysis, that's the plan, so hopefully that will be of interest. And that really just leaves me to say that if you've liked this video, please do remember to hit that like button, and if you hadn't done so already, please consider subscribing to my channel. I do try to make videos regularly. I'm deliberately not saying once a week anymore because at the moment that's just proving to be impossible, but I do my best. So if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, listen, thank you very much for watching. It's really been a great deal of pleasure making this video. I really hope you've enjoyed it and found it useful. Let me know in the comments below. And I really look forward to seeing you in the next video. Bye.